So, okay, let's start. So I think I've got most of your tests through email, which is great. Is there anyone that brought a hard copy? Okay, that's great too. Okay, so I've got everybody. It should take me a few days to work through that. So my goal for today, I want to get back into that spreadsheet, and then I want to finish chapter 6 and start chapter 7. So we've been talking about the importance of the mean and the variability around the mean. And so last class we calculated confidence intervals. And so if you have a very large population and you draw several samples from that population, you would expect the mean of each of those samples to be a little bit different from the overall population mean. And so in order to provide a more accurate picture of the population mean, we calculate a confidence interval. So we say this is the sample mean, but we can say with 95 or 99% confidence that the population mean is somewhere within these boundaries with the sample mean in the middle. So to review that and to get you to practice just a little more with stats, the first activity for today is I'd like you to go back into your spreadsheet. On Tuesday, we worked through mid-thigh circumference. So to review, we have 3 groups of lifters: bodybuilders, powerlifters, Olympic weightlifters. And we had 5 people in each group. This was a really good study because it's very hard to get elite people into a study, large numbers. So typically with studies that involve elite people or athletes, the number of people in the study is also lower. So there's just 5 in each group. What I'd like you to do is you simply scroll over, and I'd like you to do all of those same steps for body mass. So you just repeat the steps that you did for mid-thigh circumference, and I want you to go with the FAST method, like what we talked about with all of the formulas for variance and so on. So just to review, why is it that we subtract 1 from the denominator on the variance? What's the reasoning for that?
More representative of the population.
Yes, so you would expect the large population to have a lot more variability in scores around the mean versus a much smaller sample, which would be expected to have a much tighter variability around the mean. So we subtract 1 in order to get a larger number for the variance and standard deviation to be more representative of the population. So go ahead and work your way through here. So I can do this to review. So the first thing that we do whenever we want to put a formula in a cell is what? Yeah, the equal sign. So equals, and then if I'm taking a mean, what would I type in next? Yep, so I type in the average and open parentheses, and then you could simply highlight the cells that you want to take the average of, close your parentheses, and so it looks like the average or mean body mass for the bodybuilders in kilograms was 83.64. So then for variance, what is the choice that we want? I'm typing in VAR, .S, and open your parentheses. So you're just going on right down the line. So how do we define standard deviation? The square root of what? Square root of the variance. So you can either take the square root of this number, or you can just use the Excel automatic formula equals STDEV dot S to get your standard deviation. Either way, you're going to get the same number. So STDEV dot S, and then you're just highlighting your cells again, and just like that. So we can say that to describe this subset of bodybuilders, we could say the average body mass was 83.64 plus or minus 5.45 kilograms. So kind of a pretty tight distribution around the mean value. So standard error, how do I get that? So that's the square root, or the standard deviation divided by the square root, SQRT, and what's n? And yeah, that would just be the number of scores or number of people. So you just want to put 5 there. So just like that. So you're just taking S as your standard deviation. So you're just clicking on that cell, and then the square root of the number of people in your sample. Have that, and then, okay, so confidence intervals. So which table do we look at in our book? And it's going to be the same values because we have the same degrees of freedom. So good memory. Good. I actually think that is correct. So if you don't have a great memory like Jordan, and you still have, you can scroll over and look, but yeah, so 4 degrees of freedom. And why do we say two-tailed? Why do we ignore the one-tailed? We want to look in the two-tailed column because we're looking above and below the mean. So 2 different directions. So in statistics, we call that a two-tail test. So you line up 4 degrees of freedom with 0.05, which is our 95% confidence interval. And we go down and we see 2.776 is our value there. So we would then multiply the standard error of the mean, which is this, by 2.776. So it would be equals that, and then multiply by 2.776 to get your 95% confidence interval. Can you help me with the value for 99%? 4.604. 4.604. 99%. Okay. So just to be clear, 95% confidence. So this is all about trying to pinpoint where your population mean might be. So for what we just did, what was our mean? For 83.64. And so for 95% confident, what was our value for 95%? 6.76 minus 6.76. So what are your boundaries then? So what's 83.64 plus 6.76? Sorry to. Let's go ahead and help me out here.
90.4.
So 90.4, okay, and then minus 6.76 to get our lower boundary.
76.88.
Thank you, 76.888. Okay, so we can say with 95% confidence then that our population mean is somewhere between these boundaries. So I'll let you go ahead and finish out powerlifters and Olympic lifters. Is everyone clear on what confidence interval means? Okay, all right, so we're just comparing a sample with a population. So let's go ahead and get in there and finish out powerlifters and Olympic weightlifters just for practice. And you'll want to have this because on the second exam I give you some statistical questions and you can use your spreadsheet to help you on the exam. So you want to make sure you save it. So take about 5 minutes and work through the other ones. So statistics is a lot of repetition. It's the best way to learn it. You guys playing tonight?
No, we go to SBU on Saturday.
Oh, okay. Maybe the men are playing tonight.
Yeah,
Okay. Guys doing okay? With the consent?
Yeah.
Which group has the highest body mass out of these three? Do we know yet? Sydney, did you find out already? Yeah. Okay, so looks like if you look individually, it looks like that would be the case. Which group has the highest standard deviation? So which group has the highest variability? Would be my next question. Is that the book on here? Is it the same? In that book that I have, it's table 5. It is different on the There you go. So then it would be 4 degrees of freedom because 5 minus 1 is 5 in your sample. And you just go over to the 0.05. And there it is. Yep. And then for the 99%, you just go over to 0.01. That's how it works. Okay, Annalise? How? Okay. Anybody have the answer yet? The powerlifters again have the highest variability. So think of standard deviation as kind of the spread of scores. So on average, they have the most distance from the mean in their scores. How many of you need just a little more time with this part? Okay, give you a couple more minutes. Okay, Jordan? Yeah. You must teach CPR in this class. Do any of you had your CPR class in here?
It's a long Monday night.
4 hours or? Okay. So back into chapter 6. Okay, so confidence interval, we're good there. Let's talk about some assumptions with parametric statistics. 3 assumptions that we want to meet with our projects. And first one is the population from which the sample is drawn is normally distributed. So a normal distribution is sometimes called the bell curve, meaning that most of the scores will be very close to the mean. So about 68% plus or minus 1 standard deviation from the mean. And then 95% of scores plus or minus 2 standard deviations. And then 99% of scores will be within 3 standard deviations of the mean, so on either side of the mean. So all of those measures of central tendency, mean, median, and mode, are at the center of the distribution. So for any given characteristic, as we increase the size of the sample closer to the size of our population, the spread of scores approximates a bell curve. So our second one is that all of our samples drawn from the same population. So we have a large population and we're drawing several smaller samples. So what we hope is that the assumptions that we make about the population we can measure with just the sample. So it's a lot easier to measure a small sample and make assumptions about the population overall. And so we would hope that the samples that we measure from the population have the same variability. So they would have the same standard deviation. The last one is that the observations are independent. So in your own study, think about your own projects, and I'm looking forward to just looking over those because that's going to guide your decisions for the second half of the semester as you go out and pursue your own research. So the measurement of one individual shouldn't affect measurement of other individuals on a given characteristic. So your dependent variable is what you're measuring, and as you measure one person, that shouldn't influence your measurement of the next person, and so on. So for most of the research in physical activity, we assume that these assumptions have been met. So we follow standardized procedures and protocols and try to control confounding factors the best we can. So here's another slide, just what I was saying about the bell curve with the percentages and different standard deviations. Okay, so what statistics tell us? First of all, the significance. Significance is based on probability. So the probability of a chance occurrence. What does it mean for something to occur by chance? Or what would you say? What does it mean for something to occur by chance?
Luck.
Yeah, okay, at random. Okay, so that's what statistics tell us, is the probability that differences between conditions or groups occurred by chance. And so oftentimes in health and human performance, the usual level of chance occurrence is 5%. So that's why in a test of significance, we adopt a probability level of 0.05. So that's saying that 5% of the time, any observed differences are due to chance occurrence. You can look at it the other way. 95% of the time, differences are due to truth or reality. So there is real differences. The other one that I really like more than probability is the effect size. I'm hoping all of you will consider doing measure of effect size, because that tells you the magnitude of difference aside from probability. And so this has a lot of meaningfulness and practicality to it, because you're looking at actual differences rather than the probability of differences. So in Chapter 7, I'll teach you how to calculate effect size. So types of statistical techniques. We can look at relationships. And so for that, we use the Pearson R. And Excel is a really nice tool to easily calculate Pearson R's. And we'll do our second class activity here in a moment with that. Going beyond relationships, though, we have to do more extensive statistics to establish cause and effect. So with correlations, it's just the beginning of establishing cause and effect. So we can't necessarily say one variable causes another. So looking at a recent study that showed doing deep squats was inversely related to 30-meter sprint performance. So the more weight that you could use for a deep squat, defined as where the crease of the hip is below the top of the knee, the faster the times were for a 30-meter sprint. So that's a correlation. Beginning of cause and effect. So you might take a result like that and you might say, well, seems like maybe doing deep squats over a period of time would improve my 30-meter sprint performance. So we can't quite go that far, but we can say at least there's an association. To determine cause and effect, we have to look at differences between conditions or groups over time. So this is where we go to a t-test and analysis of the variance. So these are all things that we're going to do. So to start with, I think correlations would be the best place to start. So I want you to go back into your spreadsheet. And so what makes this nice is it's actual data. So go to the tab that says Main Data Sheet. Main Data Sheet. And once you get to the Main Data Sheet, I want you to scroll over and you'll see these this correlation matrix. So there's a matrix for each group. And so this matrix for bodybuilders has already been completed. So you can see all the correlations between the different anthropometric variables that were collected. So we could do this one again. Let's just put your cursor there in M2, and you can just hit delete so that it's blank. And so we're going to calculate the association between body mass and height for our bodybuilding subsample. So what's the first thing we always do?
Equals.
Yes, that's right. So equals. Now because we use Pearson most often, you can just begin typing in Pearson. And you'll see that it comes up. So it knows exactly what we're trying to do here. So if you double click on Pearson, you can see that it wants two arrays. So we want the row for body mass as array 1, and we want the row for height as array 2. So it's pretty easy. You can just scroll over and you can take your body mass here. And if you ever want to see what's going on with what you're putting into a cell, you can look up here. So I just put in E4 to E8, just highlighted that. And so then you can just put a comma, and then you can go over to height. So let's do height in centimeters. Doesn't matter if you do inches, it'll come up with the same correlation. So, and close your parentheses. So this is what you'll have in your formula bar up here. So then you can just hit enter, and you can see there it's a correlation. So slightly on the positive side, I wouldn't say super strong, but we can say maybe a trend where as height goes up, what happens to body mass? Yeah, it also goes up. So you can see some of the other ones here. That looks like a strong one right there. So as height goes up, mid-thigh skin fold also tends to go up in this population. So anything 0.6 or 0.7 is starting to get into a pretty good relationship. What other things here? So mid-thigh skin fold and percent body fat. So as percent body fat goes up, mid-thigh skin fold. So that makes sense. What else? Oh, here's one. That's a pretty strong correlation there. So that's negative 0.7. So that means that as the 1 rep max squat goes up, what happens to height? It goes down. So that intuitively that would make sense. Let's see. There's one, not real strong, but on the inverse side. So as 1 RM squat goes up, what happens to percent body fat in this group? Goes down. Okay, so let you take it away. I want you to go ahead and finish those correlation matrices for powerlifters and Olympic lifters.
Just the one that you did for the top, for all of the.
You'll do exactly what I did here for the bodybuilders, only for the powerlifters and Olympic lifters. So here's your cheat sheet, just so you can check to see if you're doing it right. So you may come back with several decimal places, so all you really need to do is highlight that cell and then just go up here to this reduce decimal places, and you could go down to 2 for that. So you could just go right up there and just click it until you get down to 2. So if you're in your project, if you're collecting lots of variables, sometimes it's useful to look at correlations. And then you could report in your results this matrix type so you can see everything all at once. Couple really strong correlations there in the Olympic lifters with the 0.8s, couple 0.8s up here. Seems like there's a consistency among lesser height means greater load on the 1 rep max for all 3 groups. Questions? Makes sense? Yeah. Excel working better?
Yeah.
Guys doing good? Me too. Does it make sense? Getting the same answers.
Pretty close.
Huh?
Yeah.
What are you doing your thesis, Shelby?
When am I doing it?
Next spring or fall?
Probably next fall.
Next fall.
Mm-hmm.
That'd probably be a good time with off season.
Mm-hmm.
So if you want to see what a thesis proposal looks like, Dr. Schaefer and I have several students tomorrow. PE building from 10 to 12:30 in room 122. So just if you're curious, you can stop by and listen to some of the proposals. So let's see, we've got Lindsay Meyer and Brian Kostelecki, Alex Garza, Trace Owens, Matthew Poor, Haley Gunter. So several of them. You ever see much of Haley anymore?
Yeah.
Occasionally.
For the gym.
Yeah. her internship this semester. Okay, how many need a little more time? Yeah. All the way down, all three of them. Just what you see up there. So it looks like with the power lifters, negative 0.85, so that's a really strong correlation for squat going up, body mass going down. So in this study, we didn't separate, well, I guess you could calculate lean body mass by multiplying body mass by the percent body fat. It looked like also though, if you look at the squat going up, the body fat percent was also going down, so that suggests maybe the leaner athletes were lifting more weight. We'll be using table 5 a lot because it's also used for t-tests we have coming up. Okay, I'm going to, you can finish up there as I'm talking. Let's get into chapter 7, basic statistics in research. Okay, so probability, basing our conclusions on probability can sometimes be good, sometimes not so good, because sometimes there are real differences between conditions that we overlook. Sometimes in reality there's no differences, but our statistical test says there is, and that could be a problem as well. So the purpose of this chapter is to help you see probability in the proper context and also introduce effect size. So we use probability statements to summarize our conclusions about our statistical test. So in HHP, the typical probability value is 0.05. So there's a 5% chance that, there's a 5% probability that results were due to chance. So, in other words, there's a 5% chance of a type 1 error. So it's important to understand what a type 1 error is. Type 1 error means that our statistical test says there are differences between conditions when in reality there is not. So differences were due to random chance. So a type 1 error can happen a lot, especially if you have a very small sample size, especially if the sample was sample that was maybe handpicked, people that maybe weren't as generalizable to the larger population. So another way of describing our probability value of 0.05 is that is the alpha level. That is the alpha level. So in a lot of studies you might read the alpha selected was p less than 0.05. So when we make a type 1 error, it's a failure to reject a true null hypothesis. So let me ask you a question. What is the null hypothesis? So in your proposal, you'll have two hypotheses. You'll have a null hypothesis and an alternative hypothesis. What is the null hypothesis? There's no differences or change between conditions or groups. So that's the reality. That's the reality. So in reality, there's no difference between our groups. So that's the truth. That's the reality. But if we fail to reject that, then we've made a type 1 error. So in other words, we are saying there's differences. Our statistical test says there are differences when in reality there's not. When the null hypothesis is true, but we fail to reject it. Okay. So in a little bit plainer terms, this is our statistical test says there is a difference. Okay, when truly or in reality there is not a difference between conditions, so differences were due to random occurrence. So another way of thinking about a type 1 error is a false positive result. False positive result. So with COVID testing, are false positives common? Yeah, so what does that mean with a COVID test, a false positive? The test says you have it, but in reality you don't. That's a type 1 error. So your test says there is something going on, but in reality there's really not. So our test can be due to our test result can be due to a random occurrence. So a false positive would be a type 1 error. Okay, so again, our typical probability is 0.05. Sometimes we go a little stricter and say 0.01. So 0.01 reduces the probability of a type 1 error because now it's not 5% chance of random occurrence, it's 1% chance of random occurrence. In other words, 99 times out of 100 results are real due to actual differences. So another way of thinking about it, 0.05, there's a 5% chance of type 1. 0.01, there's a 1% chance of a type 1 error. So another HHP application. How many have ever been tested with a screening tool? Don't we use screening tools all the time in HHP? So sometimes screening tools are used to predict the probability or risk of an injury. So you take an assessment, and based on prior research that has validated this screening tool, the score on the assessment is predictive of the probability of injury. So probably the most popular or a common one, the functional movement screen. How many have heard of that? Yeah. So your score on the functional movement screen has a certain ability to predict future occurrence of injury. So we certainly hope that athletes don't get injured. However, if you have a score on the functional movement screen that suggests that there could be a future injury, what would you do? You'd have to do some type of corrective exercise, wouldn't you? Okay. So that's why we use screening tools, is if the screening tool can identify individuals with the probability of injury, then we do corrective exercise to mediate that risk. So efficacy is really important with screening tools. Otherwise, why do we want to waste time on a screening tool if it's not very effective at predicting risk? So there are 4 terms here that you need to become familiar with. 4 terms here: true positive, false positive that we talked about just a minute ago, true negative, and false negative. Those 4 things you need to be comfortable and understand the meaning. Okay, so this is a 2x2 table. So over on the left here represents reality. Okay, so we have injuries and people that did not get injured. And across the bottom, uninjured; across the top, injured. Okay, now the first column is those who screened positive on this screening tool. Second column is those that screened negative with this screening tool. So in 2 cases, we can make a correct decision. So 2 cases we can make a correct decision. The first is with true positives. We make a correct decision because these were people that screened positive, and unfortunately, they incurred an injury. So that's a true positive result. Okay, now on the bottom here, these are uninjured, and they screened negative with our screening tool, whatever that might be. And so a true negative, they were uninjured, they screened negative, so a true negative. So that's also a correct decision. So we want our screening tools to correctly identify those that are at increased risk, in other words, our true positives, and those that are truly at decreased risk. So those are our true negatives. So the 2 other scenarios where we would make an incorrect conclusion would be a false positive. Okay. So in this case, they screened positive and they did not incur an injury. So that would be a false positive result. They screened positive, they did not incur an injury. So they would fit in this box. The other incorrect conclusion would be if they screened negative and unfortunately they incurred an injury. So that would be a false negative. So in the case of a false positive, that's a type 1 error. So our screening test was positive, saying that they had a high risk of injury, and they actually didn't have an injury, which is great. Okay, so what would be maybe the downside of incorrectly identifying an individual as high risk when they're not? So a false positive means that your screening test says they have a very high risk of injury, when in reality they are maybe not as high risk as we think. What would be perhaps maybe a disadvantage of that?
Spending time doing preventative stuff versus
Yeah.
in other places.
So you're taking like a shotgun approach where maybe you're putting people in this category into several minutes of of doing correctives or preventatives when they could be doing other stuff. Okay, so that's a disadvantage. Okay, what about over here? Screening negative, but they actually had an injury. So over here, you're incorrectly identifying people as low risk. So what's the disadvantage there? You're putting someone in a low risk category when they shouldn't be. So these are the people that probably should be doing correctives. So your test incorrectly identified those people as being low risk when in actuality they were a high risk. So that's what we call a type 2 error. So I want you to just kind of get it straight in your mind, go over it again. Type 1 error means our test says yes, but in reality there's not a risk or a difference. Type 2 error, our test says no, there's not a risk or there's not a difference, when in actuality there is. So in either case, we put people in a category they shouldn't be in. So a couple of terms that are associated with this 2x2 table. So sensitivity of the test is the percentage of true positives. So if you took all the people across this row, all the people that got injured, and you divide your true positives by the total people in this row, your true positives plus your false negatives, that would give you your sensitivity, your percentage of true positives. So ideally, you want to have an effective screening tool. You want people here, and you want people here, because then you can correctly do things to mediate those risks. You don't want people in the false positive or false negative categories. So sensitivity is your percentage of true positives. Specificity, on the other hand, is your percentage of true negatives. So how many people were cleared? What does it mean to be cleared by a test? Good to go. That's a great, I like that. Good to go. So screen negative, you're good to go. That's specificity, your percentage of true negatives. So you take your true negatives and then you'd add up all the people across this row, your false positives and your true negatives together. So it's your percentage of people that are good to go. So ideally, you want people in the true positive category that you can prescribe corrective, preventative type exercise, or you want people in the true negative category that can prioritize other things other than incorrectly being identified as false positive and doing a lot of things that maybe aren't the best use of time. So just a little bit more explanation on sensitivity. So just what Bryant said there, a test with poor sensitivity would incorrectly place many athletes into a low risk category. Specificity, on the other hand, is the ability to correctly clear a group of athletes. So important to have a high specificity to avoid incorrectly categorizing an athlete into high risk when they shouldn't be. So if an athlete's not high risk, they can be doing things to improve strength, power, conditioning, rather than specific injury prevention exercises. So we only want injury prevention if there's a need for it. That's why we have screening tools, is to identify those that need to be doing the correctives, is the purpose. Otherwise, why do we do screening? I mean, that's the purpose. Okay, so I'll give you another example. So all of you at some point will be in this position, hopefully. March 9th, 2002, so mine is coming up. So Okay, so will you marry me? I fail to reject the null hypothesis. So, null hypothesis is a negative. That means no change in status. So if you fail to reject something, what are you actually doing? You're accepting it, so she said no. Okay, so alpha is the type 1 error rate. Beta is the type 2 error rate. Beta is the type 2 error rate. So think about this, failure to reject a false null hypothesis. So if the null is false, what does that mean for differences between conditions? If in reality the null is false. So if the null hypothesis says there's no difference, but if the null is false, what does that mean? There are differences. So failure to reject the null hypothesis would give you a type 2 error. So what would be maybe the disadvantage, or what would be the implications of a type 2 error maybe for drug treatment for different medical conditions like cancer? We would say that treatment wouldn't work, but in reality, it does. So that's the key downside. Is maybe the testing on a particular sample says there is no difference in treatment outcomes when in reality there are differences. So that would be a type 2 error. So a type 2 error is what we talked about, a false negative, saying there's no difference between conditions when in reality there are. So there's a trade-off here between alpha and beta. So in other words, there's a trade-off between the chance of making a type 1 error and the chance of making a type 2 error. So think about it, as your alpha goes up from 0.05 to 0.01, we go from a 5% chance of a type 1 error to 1% chance of a type 1 error. But at the same time, if we're really strict like that, what could we be missing? We could be missing actual differences that are meaningful. So as the type 1, as the alpha becomes increasingly more strict, we have a greater chance of making a type 2 error where we miss meaningful differences, is the point. So typically we say 0.05. And then in addition to 0.05, we also do effect size to look at actual differences between groups. Okay. So we'll do Yoda next class. But does anybody have any questions? Everybody understand what true positive, true negative, false positive, false negative is? Everybody understand what a type 1 error is? Type 2 error. Can you do a correlation? Okay, all right, so let's end right there for today. I'll get your test corrected. So Tuesday we'll continue with chapter 7. Have a great weekend.